January 17, 1991, 1:30 a.m. Baghdad local time. In the fortified command bunker beneath the Iraqi Ministry of Defense, officers monitored radar screens that showed nothing unusual. Air defense networks stretched across the nation in overlapping layers. Surface-to-air missile batteries ringed every strategic facility. Early warning radars swept the horizons. The bunker itself sat behind meters of reinforced concrete, designed to withstand direct hits from conventional bombs. Confidence filled the room. Saddam Hussein's military leadership had spent billions on Soviet air defense systems, creating what they believed was an impenetrable shield. Intelligence assessments concluded that any American air campaign would suffer catastrophic losses attempting to penetrate Baghdad's defenses. Then, without warning, the ceiling disintegrated. A Tomahawk cruise missile, launched from the USS San Jacinto operating 700 miles away in the Red Sea, had just completed a flight of over an hour, navigating at treetop level through the night, invisible to radar, following terrain contours with mechanical precision, and detonating its 1,000-pound warhead exactly where mission planners in the United States had designated weeks earlier. The Iraqi officers never saw it coming. Within the first 90 minutes of Operation Desert Storm, 122 Tomahawk missiles struck command centers, communications nodes, and air defense headquarters across Iraq, launched from cruisers, destroyers, and battleships positioned hundreds of miles offshore. The assumption that distance and fortification provided safety had just been obliterated. The arrogance was not uniquely Iraqi. Throughout the 1980s, Soviet military theorists and their client states operated under a fundamental assumption about modern warfare. Strategic targets deep inside a nation's territory were protected by distance, early warning systems, and layered air defenses. Warsaw Pact doctrine emphasized that any NATO air campaign would require massed formations of strike aircraft penetrating defended airspace, suffering attrition rates that would make sustained operations impossible. Soviet air defense doctrine, exported to Iraq, Syria, Libya, and other allies, assumed that surface-to-air missiles and interceptor aircraft would exact unacceptable costs on any attacker. The mathematics seemed irrefutable. A fighter bomber carried perhaps 2 precision-guided munitions and required air superiority, electronic warfare support, tanker aircraft for refueling, and search-and-rescue assets standing by. Each sortie risked a multi-million-dollar aircraft and a highly trained crew. Defending forces only needed to make the cost of attack exceed its value. Iraqi Air Force officers trained in Soviet academies calculated that American forces would lose dozens of aircraft in the opening days of any conflict, creating political pressure to halt operations before strategic objectives could be achieved. Internal Iraqi military assessments from late 1990, captured after Desert Storm, revealed supreme confidence. One planning document stated that American forces lacked the capability to conduct sustained precision strikes against hardened facilities without suffering losses that their public will not tolerate. Another assessment concluded that cruise missiles, while technologically interesting, lack the payload and accuracy to threaten strategic facilities and can be intercepted by conventional air defenses. These were not irrational conclusions based on the information available to Iraqi commanders. Cruise missiles had existed since World War II in primitive forms. The Soviet Union had deployed anti-ship cruise missiles extensively, but land attack cruise missiles capable of flying 1,000 miles to hit a specific building had never been proven in combat. Iraqi planners assumed, as Soviet doctrine taught them, that such weapons would be inaccurate, easily detected, and vulnerable to interception. The weapon that shattered these assumptions had been in development since the mid-1970s. Born from a U.S. Navy requirement for a long-range strike capability that could be launched from surface ships and submarines without requiring air superiority or placing manned aircraft at risk. The BGM-109 Tomahawk land attack missile program began as a response to a fundamental strategic problem: how to hold Soviet targets at risk without depending on increasingly vulnerable bomber fleets or exposing carrier battle groups to anti-ship missiles. General Dynamics initially developed the system, later transferred to McDonnell Douglas, and ultimately to Raytheon. The first test flights occurred in 1976. Initial operational capability for the nuclear-armed version came in 1984. The conventional land attack variant, which would revolutionize strike warfare, achieved initial operational capability in 1986, but technological maturity and combat readiness were different thresholds. By January 1991, when Operation Desert Storm commenced, the Navy had deployed Tomahawks on cruisers, destroyers, battleships, and attack submarines, yet no Tomahawk had ever been fired in combat. The system remained unproven. Critics within the defense establishment questioned whether the missile's guidance systems would function reliably under battlefield conditions, whether enemy electronic warfare could disrupt navigation, and whether the 1,000-pound conventional warhead carried sufficient destructive power to justify the cost of approximately $1.3 million per missile. Iraqi commanders, reading the same defense journals and intelligence reports, assumed American planners would hesitate to employ an unproven, expensive system in large numbers. What Iraqi intelligence failed to comprehend was the engineering revolution contained within the Tomahawk's guidance section. The missile employed three integrated navigation systems, each compensating for the limitations of the others, creating a level of precision and reliability unprecedented in autonomous weapons. The primary navigation system was an inertial measurement unit consisting of three-ring laser gyroscopes and three accelerometers, tracking the missile's position in three-dimensional space from the moment of launch. Inertial navigation alone, however, accumulated errors over long flight times, with position uncertainty growing to approximately 0.8 kilometers for every hour of flight. For a 500-mile mission lasting roughly 90 minutes, pure inertial navigation would produce unacceptable targeting errors. The breakthrough came with TERCOM, terrain contour matching. Before each mission, planners loaded a digital terrain map of the missile's flight path into the weapon's computer memory. As the Tomahawk flew, a radar altimeter continuously measured the ground elevation beneath the missile. The onboard computer compared this real-time terrain profile against the stored reference map. When the measured contours matched a known section of terrain, the missile's inertial navigation system received a position update, correcting accumulated drift. TERCOM updates occurred at predetermined checkpoints along the route, typically every 50 to 100 miles, ensuring the missile remained on course. The system worked by flying at extremely low altitudes, typically 50 to 200 feet above ground, hugging terrain features to avoid radar detection while simultaneously using those features for navigation. This was not approximate navigation. TERCOM provided position accuracy within 30 meters, repeatedly throughout flights lasting over an hour. For terminal guidance during the final approach to the target, the Tomahawk employed DSMAC, digital scene matching area correlation. Intelligence agencies photographed the target area from satellites or reconnaissance aircraft, creating high-resolution digital images of distinctive terrain features, buildings, roads, or other landmarks near the target. These reference images were loaded into the missile's memory. As the Tomahawk approached the target area, an onboard optical camera captured real-time images of the ground below. An image processing computer compared the live camera feed against the stored reference images. When correlation exceeded a threshold, indicating the missile had positively identified its position relative to known landmarks, the guidance system commanded final course corrections. DSMAC operated in the final 20 to 30 miles of flight, providing accuracy measured in meters. The camera system functioned in daylight and with later upgrades in infrared for night missions. The processing occurred entirely onboard the missile, requiring no external signals that could be jammed or intercepted. Block II Tomahawks, which comprised the majority of missiles fired in Desert Storm, carried CCD cameras operating at approximately 100 knots ground speed, capturing and correlating images in real time while flying at altitudes below 100 feet. Block III variants, introduced in 1994, added GPS receivers, providing continuous navigation updates independent of terrain features, but the GPS constellation was not yet fully operational in January 1991. Desert Storm Tomahawks relied primarily on TERCOM and DSMAC, autonomous systems immune to jamming. The physical design of the Tomahawk reflected an obsessive focus on low observability and fuel efficiency. The missile measured 18 feet 3 inches in length without the booster, 20 feet 6 inches with the solid fuel booster attached. Diameter was a compact 20.4 inches, allowing it to fit within standard submarine torpedo tubes and vertical launch cells on surface ships. Wingspan extended to 8 feet 9 inches after deployment, but the wings folded flat against the fuselage during storage and launch. Weight totaled approximately 2,900 pounds without booster, 3,500 pounds with booster. After launch, a solid fuel rocket motor burned for roughly 12 seconds, accelerating the missile to cruise speed before separating. A Williams International F107WR402 turbofan engine, producing 600 pounds of thrust, sustained flight for the duration of the mission. The engine consumed JP-10 fuel stored in internal tanks, providing enough range for missions exceeding 1,000 nautical miles. Cruise speed held steady at approximately 550 miles per hour, subsonic to minimize acoustic signature and reduce infrared emissions. The radar cross-section, while not approaching stealth aircraft levels, was significantly reduced compared to traditional cruise missiles through shaping and materials. The missile's small size, low-altitude flight profile, and subsonic speed made it extraordinarily difficult to detect and track with 1980s-era radar systems. The warhead bay accommodated either a W-80 nuclear warhead with a yield of 5 to 150 kilotons for strategic missions, or a 1,000-pound conventional unitary penetrating warhead for land attack missions against hardened targets. An alternative conventional payload consisted of a submunitions dispenser carrying 166 combined-effect bomblets for area targets. The unitary warhead variant, designated the WDU-36B, was optimized for penetrating reinforced concrete before detonation, designed specifically to destroy bunkers, command centers, and hardened aircraft shelters. The fusing system allowed for surface detonation, delayed detonation after penetration, or airburst selectable during mission planning based on target characteristics. This versatility meant a single weapon type could engage underground command bunkers, communications towers, power stations, or troop concentrations with appropriate fusing and warhead selection. Iraqi defense planners, accustomed to Soviet-style mass attacks with unguided munitions, failed to appreciate that a single Tomahawk, properly employed, could achieve effects previously requiring dozens of bomber sorties. Deployment of the Tomahawk required significant naval assets and logistics. Surface ships employed the Mk-143 armored box launcher, a four-cell containerized system installed on battleships and early Aegis cruisers, or the Mk-41 vertical launching system, a multi-cell system integrated into the hull of Ticonderoga-class cruisers and Arleigh Burke-class destroyers. Each Mk-41 module contained 8 cells in 2 rows of 4, and ships typically carried multiple modules. A Ticonderoga-class cruiser could embark up to 122 missiles in its Mk-41 system, a mix of Tomahawks, standard surface-to-air missiles, and ASROC anti-submarine weapons. The vertical launch system used a cold launch method. High-pressure gas ejected the missile from the cell. The booster ignited after the weapon cleared the ship, preventing rocket exhaust from damaging the launch cell or adjacent missiles. This allowed rapid salvo launches, with multiple Tomahawks launched seconds apart. Submarines employed either torpedo tube launches using a capsule system or dedicated vertical launch system tubes integrated into the hull forward of the sail. Lowe's Angels-class attack submarines carried 12 vertical launch tubes for Tomahawks in addition to their torpedo tubes. Ohio-class guided missile submarines, converted from ballistic missile submarines beginning in the 2000s, carried 154 Tomahawks, but these conversions were not yet operational in 1991. For Desert Storm, surface combatants carried the majority of the Tomahawk load. Mission planning for Tomahawk strikes required extraordinary precision and intelligence. Weeks before the start of air operations, naval strike planners worked with intelligence agencies to select targets, develop flight routes, and generate mission files for each missile. Satellites, U-2 reconnaissance aircraft, and human intelligence sources provided targeting data, GPS coordinates, building layouts, structural assessments, and defensive systems. Each missile received a unique mission profile. The flight path avoided known air defense concentrations when possible, used terrain masking to minimize radar exposure, and included multiple TERCOM and DSMAC checkpoints. Routes often covered distances far exceeding the straight-line range to the target, with missiles flying circuitous paths to approach from unexpected directions. Planners identified distinctive terrain features along each route and extracted terrain elevation profiles from Defense Mapping Agency databases. DSMAC reference images came from satellite photography, carefully selected to show high-contrast features unlikely to change: riverbends, road intersections, distinctive buildings. The mission data was encoded onto a data module, essentially a removable hard drive, which technicians installed into the missile before loading it into the launch cell. This process meant each Tomahawk was a custom weapon programmed for a specific target via a specific route, not a general-purpose munition. If you appreciate discovering Cold War secrets hidden for decades, consider subscribing for future declassified revelations. The infrastructure supporting Tomahawk operations extended far beyond the launch platforms themselves. The Theater Mission Planning Center, a sophisticated computer facility, processed intelligence data, and generated the terrain maps and DSMAC imagery required for mission planning. Afloat planning systems aboard command ships allowed limited mission updates and retargeting, though the technology of 1991 did not yet permit in-flight retargeting. That capability would arrive with Block IV missiles in the 2000s. Communication networks linked the planning centers with launch platforms, transmitting mission orders and launch authorization codes. The entire system represented an integration of space-based reconnaissance, signals intelligence, computational cartography, precision engineering, and network command and control unprecedented in military history. Iraqi commanders understood American technological sophistication in individual domains but failed to grasp how integration multiplied capability. A satellite alone was impressive but finite in effect. A cruise missile alone was interesting but unproven. Network systems feeding precision intelligence into autonomous weapons launched from platforms 700 miles away created effects beyond the sum of components. At 300 hours on January 17, 1991, the guided missile cruiser USS San Jacinto, operating in the Red Sea approximately 700 miles from Baghdad, received launch authorization. Minutes earlier, USS Bunker Hill in the Arabian Gulf had fired the first Tomahawk of the war toward targets in southern Iraq. Within the next 2 hours, 9 ships in the Red Sea, Arabian Gulf, and Eastern Mediterranean launched 122 Tomahawks against 16 high-value targets in Iraq. The missiles rose from vertical launch cells on geysers of gas pressure, solid rocket boosters ignited, wings deployed, and the weapons turned toward their programmed routes. Sailors watched the missiles disappear into the darkness, their turbofan engines emitting low rumbles that faded within seconds. The launch platforms maneuvered to unmask additional cells and prepared follow-on salvos. No enemy action interfered with the launches. Iraqi air defenses had no awareness the attacks were underway. The Tomahawks flew low over water, their small radar cross-sections and sea-skimming profiles rendering them effectively invisible to surveillance radars designed to detect high-altitude aircraft. As the weapons transitioned from overwater flight to land, they descended to altitudes below 100 feet, using wadis, riverbeds, and low terrain to mask their approach. Iraqi air defense radars, positioned to detect aircraft at medium and high altitudes, looked over the missiles. Even when radars momentarily detected a low-altitude contact, operators dismissed the returns as ground clutter or birds, not recognizing the signature of an inbound cruise missile because they had no experience with such threats. The first Tomahawk impacts occurred at approximately 300 local time, moments after H-hour, the designated start of air operations. Baghdad's main telephone exchange, a key communications node linking military command centers, erupted in flame as a 1,000-pound penetrating warhead detonated inside the building after smashing through the roof. Air defense operators attempting to coordinate responses found their telephone networks dead. Seconds later, the Ministry of Defense headquarters absorbed multiple Tomahawk strikes in rapid succession. The missiles arrived from different directions, having flown separate routes converging on the target, overwhelming any possibility of intercept. Reinforced concrete walls designed to withstand aerial bombing provided no protection against warheads programmed to penetrate before detonation. Subsequent battle damage assessment, conducted days later by reconnaissance satellites and aircraft, showed catastrophic structural damage. Iraqi military communications, centralized in a Soviet-style architecture dependent on key nodes, collapsed within the first hour of the war. Regional command centers attempting to issue orders to air defense units and fighter squadrons found themselves isolated, unable to coordinate responses. This was not merely destruction of buildings, it was decapitation of command and control, rendering Iraqi forces blind and mute. As dawn broke over Baghdad on January 17, government radio broadcasts claimed that Iraqi air defenses had shot down dozens of American aircraft and that the nation's military remained intact and ready for combat. The reality visible to residents of the capital told a different story. The presidential palace smoldered, its northern wing collapsed. The Ba'ath Party headquarters stood gutted, fires still burning in the wreckage. Power stations across the city had been struck with surgical precision, plunging entire districts into darkness. Bridges over the Tigris remained standing, but military command bunkers on both banks had been reduced to rubble. Citizens who ventured into the streets after the initial strikes reported seeing no aircraft wreckage, no parachutes from downed pilots, no evidence of the aerial battle Iraqi propaganda claimed. What they did not know, because Iraqi military censorship suppressed the information for weeks, was that the destruction had been delivered by unmanned missiles launched from ships they could not see, operating from distances they could not comprehend, guided by systems they did not know existed. The psychological impact of this realization, when it finally penetrated military and civilian consciousness, was profound. If the Americans could destroy any target at any time without risking pilots or aircraft, what defense was possible? On January 19, 1991, Day 3 of Desert Storm, two Los Angeles-class attack submarines made history. USS Louisville, operating submerged in the Red Sea, launched 8 Tomahawk missiles from its vertical launch tubes, the first submarine-launched land attack cruise missiles ever fired in combat. USS Pittsburgh, patrolling the eastern Mediterranean, launched 4 more from depths exceeding 100 feet. The missiles burst from the ocean's surface in capsules that separated after clearing the water, boosters ignited, and the weapons transitioned to cruise flight while the submarines slipped back into deep water undetected. This development added a dimension to Tomahawk employment that Iraqi forces could not counter. Surface ships, while difficult to target, could theoretically be located and attacked by aircraft or anti-ship missiles. Submarines were invisible. An Iraqi commander could see no ships on the horizon, detect no aircraft overhead, observe no warning signs whatsoever, and still have his headquarters obliterated by a Tomahawk launch from a submarine 600 miles away. The submarines could reposition after launching, making location and counterattack impossible. This created a permanent threat that could never be relaxed. Iraqi forces had to assume that at any moment any facility could be struck, and there was nothing they could do to prevent it. The operational statistics from Desert Storm told a story of technological dominance. Of 297 Tomahawks launched during the 43-day campaign, 282 successfully began their missions, a 95% launch success rate. 9 missiles failed to leave their launch tubes due to mechanical issues, and 6 fell into the water shortly after launch when boosters malfunctioned. But these failures occurred before the weapons entered enemy airspace and posed no risk to crews or platforms. Of the 282 missiles that successfully launched, post-war analysis indicated that approximately 245 reached their target areas and detonated, an 85% mission success rate. The remaining missiles were lost to navigation failures, guidance malfunctions, or in rare cases, interception by air defenses. Iraqi forces claim to have shot down dozens of Tomahawks, but post-war investigations confirmed only a handful of successful intercepts, most by anti-aircraft artillery firing blind barrages into areas where missiles had been reported, achieving hits through volume of fire rather than directed targeting. The success rate compared extraordinarily favorably to manned aircraft operations. Navy strike aircraft during Desert Storm achieved target impact rates of approximately 70 to 75%, with losses due to enemy action, mechanical failures, navigation errors, and weather. The Tomahawk, immune to weather, fatigue, and fear, operating autonomously from launch to impact, proved more reliable than human-crewed systems for strategic strikes against fixed, heavily defended targets. Iraqi military records captured after the 2003 invasion provided insight into how Tomahawk strikes affected Iraqi defensive planning during Desert Storm. One document, a situation report from the Iraqi Air Force headquarters dated January 20, 1991, stated, "Our air defense forces are unable to detect or intercept the cruise missiles being employed by American naval forces. These weapons approach at altitudes below the minimum engagement envelope of our SAM systems and are too small and fast to be engaged effectively by anti-aircraft artillery. We assess that defense against these weapons is not possible with current systems." Another document from the Republican Guard Command noted, "American cruise missile strikes have destroyed 3 divisional headquarters and multiple communication centers. Our ability to coordinate multi-division operations has been degraded. We cannot predict when or where the next strikes will occur, creating constant uncertainty in command elements." These were not the words of a confident military expecting to inflict heavy casualties on an overconfident enemy. They were the assessments of a force that had been technologically outmatched and psychologically shaken. The realization that American forces could strike any target, at any time, with precision and impunity, without warning and without losses, undermined Iraqi command confidence in their ability to conduct sustained operations. Yet no one expected what would happen next. The Tomahawk's success in Desert Storm triggered a revolution in military thinking that extended far beyond the U.S. Navy. Air Force planners, observing Tomahawk effectiveness, accelerated programs for their own cruise missiles, leading to development of the AGM-86C conventional air-launched cruise missile and later the AGM-158 JASSM. Army interest in long-range precision fires, dormant since the retirement of the Pershing II missile, revived, eventually leading to hypersonic weapons programs decades later. Allied nations, witnessing Tomahawk operations, purchased the system under foreign military sales programs. The United Kingdom integrated Tomahawks onto Royal Navy submarines beginning in the late 1990s. Adversary nations drew their own conclusions. Soviet military observers embedded with Iraqi forces during Desert Storm filed detailed reports on Tomahawk capabilities. These assessments informed Russian cruise missile development, leading to systems like the Caliber, which employs similar guidance principles and mission profiles. Chinese military analysts studied Desert Storm extensively, recognizing that cruise missiles provided a means to hold high-value targets at risk without requiring air superiority, leading to development of the CJ-10 and other land attack cruise missiles. The proliferation of precision-guided cruise missiles can be traced directly to the demonstration of effectiveness provided by Tomahawks in January 1991. The Tomahawk evolved significantly in the decades following Desert Storm, but the fundamental concept remained unchanged. Block III missiles, introduced in 1994, incorporated GPS navigation, dramatically improving accuracy and allowing engagement of targets in areas without distinctive terrain features, such as deserts or flat plains, where TERCOM and DSMAC were less effective. Block IV, designated Tactical Tomahawk, achieved initial operational capability in 2004 and introduced in-flight retargeting via satellite data link, allowing commanders to redirect missiles to new targets or abort missions after launch. An onboard camera transmitted real-time imagery back to the launch platform, enabling battle damage assessment and confirmation of target identification before warhead detonation. Block IV also introduced a loiter capability, allowing the missile to circle a target area for extended periods, waiting for optimal strike conditions or updated targeting information. Block V, under development in the 2020s, adds enhanced anti-ship capabilities, multi-mode seekers, and improved electronic warfare resistance. Each evolution increased capability, but the core value proposition remained the same: precision strike against high-value targets from standoff range without risk to platforms or crews, with reliability approaching certainty. The operational employment of Tomahawks became routine in U.S. military operations following Desert Storm. In January 1993, 46 Tomahawks struck the Zafraniya nuclear fabrication facility outside Baghdad in response to Iraqi refusal to comply with UN weapons inspections. In June 1993, 23 Tomahawks hit the Iraqi intelligence service headquarters in retaliation for a suspected assassination plot against former President George H.W. Bush. In September 1995, 13 Tomahawks struck Bosnian Serb air defense sites during Operation Deliberate Force. In September 1996, 44 Tomahawks hit Iraqi air defense installations during Operation Desert Strike. In August 1998, 75 Tomahawks struck terrorist training camps in Afghanistan in retaliation for embassy bombings in Kenya and Tanzania. In December 1998, 325 Tomahawks were fired during Operation Desert Fox, a 4-day air campaign against Iraqi WMD facilities and military infrastructure. The missile transitioned from an unproven experimental system to the preferred option for opening strikes in major operations, and for limited retaliatory actions where political considerations precluded large-scale military deployments. The weapon's ability to deliver precise, devastating strikes without placing American personnel at risk made it politically acceptable in situations where ground invasions or sustained air campaigns would have faced domestic opposition. Operation Iraqi Freedom in March 2003 saw the largest employment of Tomahawks since Desert Storm. More than 800 missiles were launched during the first weeks of the campaign, striking leadership targets, air defense nodes, communications facilities, and military headquarters across Iraq. The opening strike of the war, an attempt to kill Saddam Hussein at a suspected location near Baghdad, involved a salvo of Tomahawks launched from ships and submarines coordinated with precision-guided bombs dropped by F-117 stealth fighters. The strike destroyed the targeted compound but did not kill Hussein, who had moved locations shortly before the attack, illustrating both the weapon's precision and the limits of intelligence. Throughout the campaign, Tomahawks provided theater commanders with a responsive strike capability independent of airfield availability, tanker support, or weather conditions. Submarines operating in the eastern Mediterranean and the Red Sea launched missiles that flew over Saudi Arabia and Jordan to strike targets in Baghdad and northern Iraq, demonstrating the system's strategic reach. Surface combatants in the Arabian Gulf provided persistent strike capacity, reloading Tomahawks from ammunition ships and maintaining readiness for time-sensitive targets throughout the campaign. Beyond major combat operations, Tomahawks became the weapon of choice for counterterrorism strikes and limited military actions. In September 2014, Tomahawks opened U.S. air operations against ISIS in Syria, striking command centers and training camps in the opening hours of the campaign. In April 2017, 59 Tomahawks struck Sharet Air Base in Syria in response to chemical weapons use by the Assad regime, destroying aircraft, hardened aircraft shelters, fuel facilities, and air defense systems. In April 2018, a coordinated strike by U.S., British, and French forces employed over 100 Tomahawks and air-launched cruise missiles against Syrian chemical weapons facilities. In October 2023, U.S. Navy destroyers launched Tomahawks against Houthi radar sites and missile storage facilities in Yemen in response to attacks on commercial shipping in the Red Sea. Each employment reinforced the pattern established in 1991, when American decision-makers required precision strikes against defended targets with minimal risk and maximum political control. Tomahawks were the default choice. The industrial and logistical implications of Tomahawk production and sustainment reveal the depth of American commitment to the system. Raytheon, which acquired the program from General Dynamics via McDonnell Douglas, produced over 4,000 Tomahawks between initial production in the early 1980s and the mid-2020s. Peak production occurred in the late 1990s and early 2000s, with manufacturing rates exceeding 200 missiles per year. The missiles have a designed service life of 30 years, with periodic recertification and component replacement extending operational viability. This created a challenge familiar to defense logistics, balancing production, inventory, and operational expenditure. Tomahawks fired in combat operations depleted inventory, requiring procurement to replace expended assets, but demand fluctuated wildly based on operational tempo. Desert Storm expended 297 missiles in 43 days. The following decades saw usage rates below 100 missiles per year. Desert Fox in 1998 expended 325 in 4 days, exhausting available inventory and forcing curtailment of the campaign until stocks could be replenished from production lines. Iraqi Freedom in 2003 expended over 800, again straining inventories. The challenge intensified in the 2010s and 2020s as older Block II and Block III missiles reached end-of-service life and were retired, while production of Block IV and Block V remained limited by budget constraints. By 2024, concerns emerged about Tomahawk inventory levels following sustained operations against Houthi targets in Yemen, with some estimates suggesting the Navy had expended several years of production in a matter of months. The strategic calculus surrounding Tomahawk employment evolved as adversaries adapted. In 1991, Iraqi air defenses were unprepared for low-altitude cruise missiles and achieved minimal intercepts. By the 2000s, adversaries had studied American tactics and developed countermeasures. Modern integrated air defense systems, such as Russia's S-400 and China's HQ-9, include engagement modes specifically designed to target cruise missiles, employing low-altitude radars, short-range interceptor missiles, and automated fire control systems optimized for small, low-flying targets. Electronic warfare systems attempt to jam GPS signals, degrading navigation accuracy. Adversaries employ decoys, camouflage, and rapid relocation of high-value assets to complicate targeting. Yet the fundamental advantage remains. A Tomahawk costs approximately $2 million in current-generation variants, while the integrated air defense systems required to reliably intercept it cost tens or hundreds of millions of dollars. A salvo of 20 Tomahawks approaching from multiple directions can overwhelm even sophisticated defenses through sheer volume, and the launch platforms remain beyond retaliation. The cost-exchange ratio favors the attacker, a reversal of traditional offensive-defensive calculations. The second and third-order effects of Tomahawk capability extended into strategic deterrence and alliance dynamics. The weapon provided American decision-makers with a military option between diplomatic protest and full-scale war, a capability to impose costs on adversaries without committing ground forces or risking significant casualties. This shaped adversary behavior. Saddam Hussein's Iraq repeatedly backed down from confrontations with the United States in the 1990s, after limited Tomahawk strikes demonstrated American willingness and capability to hit targets at will. Syrian use of chemical weapons declined after Tomahawk strikes on production facilities demonstrated consequences. The knowledge that American submarines could be operating undetected anywhere in the world's oceans, each carrying over 100 Tomahawks capable of striking targets 1,000 miles inland, created a persistent deterrent effect. For allies, Tomahawk capability reinforced confidence in American security commitments. NATO members in the Mediterranean and Persian Gulf witnessed American power projection independent of local basing, reducing vulnerability to host nation political pressures. Japan and South Korea observed that American naval forces could hold North Korean targets at risk without requiring use of air bases on their territory, reducing their political exposure. The Tomahawk became not just a tactical weapon but a strategic instrument of national policy. Join us here at Classified Warfare as we uncover the operations and technologies that kept the world on the brink. The night of January 17, 1991, marked a threshold in military history that adversaries still struggle to comprehend. Iraqi commanders, confident in their defenses and dismissive of American technological claims, learned that distance no longer protected strategic assets, that fortification no longer guaranteed survival, and that invisibility to radar meant invisibility to retaliation. The Tomahawk demonstrated that precision, persistence, and standoff range could be combined in a single autonomous weapon system, fundamentally altering the calculus of modern warfare. When those missiles erupted from vertical launch cells on darkened ships hundreds of miles offshore, navigated through the night by computers comparing terrain profiles and digital photographs, and detonated inside fortified bunkers that generals believed were untouchable, they delivered more than explosive warheads. They delivered the message that technological superiority had reached a level where traditional concepts of defense had become obsolete. The adversaries who assumed concrete and distance would protect them discovered in the most violent way possible that in the age of precision strike there is no safe haven. The bunkers that offered psychological comfort, the command centers that radiated authority, the defensive systems that promised security, all reduced to rubble by weapons their defenders never saw coming, launched from platforms they could never reach, guided by systems they did not understand existed. That realization, the moment when confidence collapsed into comprehension of total vulnerability, was the Tomahawk's most devastating impact. It was not merely a military defeat, it was the destruction of certainty itself.